We're going to talk about symmetry today, and just a little bit of review of polygons before we get into the actual symmetry. The good news is that you've probably studied some symmetry before in your earlier classes, but a polygon is a two-dimensional figure created by straight lines. So some examples include triangles, quadrilaterals, pentagons, and hexagons. If all of the sides in a polygon are congruent, and all of the angles in the polygon are congruent, we will be working with a regular polygon. So all the sides are the same length, all the angles are the same measure. Regular polygons are either convex, there's no angles pointing inward, or they're a star. Any other polygons are irregular. So if we look to the left on our paper, we see a regular pentagon because all of the sides are the same length and all of the angles are the same measure. In the middle is the irregular pentagon. We have straight lines, but we can tell by looking at it, first of all, that the side lengths aren't the same length. But even more so, we have an angle that points in towards the polygon instead of going outside of it. And then finally, to the far right is our star polygon, which is a regular polygon. And even though we do have indentations in here, it kind of goes back in there, it's still considered to be a regular polygon when it's a shape of a star. Again, symmetry, you've probably seen it in previous math classes. If you recall, when figures have line symmetry, what happens is we can fold the figure in half, and one half will land directly on the other half. The two halves match exactly. When finding the line symmetry of a regular polygon, the number of lines symmetry the figure has is equal to the number of sides. So I kind of went too fast on that. In a regular polygon, it will have line symmetry, and the number of lines of symmetry in the polygon is the same number as the number of sides in the polygon. And we'll see that in an example here in a minute, but actually in words here. For example, a regular octagon. An octagon being a figure that looks like a stop sign will have 8 lines of symmetry because an octagon has 8 sides. The number of lines of symmetry of a star polygon is equal to the number of its outward vertices. If you look back up at our star polygon here, 1, 2, 3, 4, 5, 6. Those are our outward vertices. So if we were to draw the line symmetry in that picture, we would have 6 lines of symmetry. Well, let's look at a couple of examples here. It says determine if the figures below have line symmetry, and then draw all lines of symmetry and state the number of lines. Well, the first picture is clearly marked as 3 congruent sides, 3 congruent angles, also known as an equilateral triangle. And because it's a regular polygon, we're going to have 3 lines of symmetry because there are 3 sides in this picture. And we can draw in those lines. There's one. Here's the second. And here's the third. It went from a vertex to the other side. These do happen to meet in the middle, although we won't dwell on that fact today. But again, a regular polygon will have the same number of lines of symmetry as it has sides. So if we look at letter B here, we have a pentagon. A regular pentagon, in fact. We have 1, 2, 3, 4, 5 sides in this figure. So we have 5 lines of symmetry. In general, the way I look at it is there's usually one line of symmetry that's fairly obvious to you. For me, in this case, it's kind of right down the middle. And again, think about the line of symmetry. If we fold that figure in half, and my line's a little bit crooked, but if we fold that in half, the right side of the picture would land on the left side of the picture. But then repeat the pattern with the other vertices. So if we look at the second vertice there, scoot that up a little bit, there's another line of symmetry. Follow the same pattern. We went the vertical vertex to the other side, in the vertex to the other side, in the vertex to the other side, and the vertex to the other side. And with the board being just a slight disoriented, I've got a big point there in the middle. But there are our lines of symmetry. What we haven't talked about is we haven't talked about something that's not a polygon, because letter C is not, it's a heart. And a polygon needs to have straight lines to create the figure. But we can still have symmetry in a heart, even though it's not a polygon. In this case, there seems to be only one line of symmetry. Again, we can fold the right half of the heart onto the left side, and it will land exactly there. Another irregular. It's a pentagon. There's 5 sides there, and we actually do have at least one line of symmetry. It happens to be here. And in fact, that's going to be the only line of symmetry in this case. When we look at the star polygon, another regular polygon here, remember that how many lines of symmetry in a star polygon is determined by these outward facing vertices. So we have 5, we're going to have 5 lines of symmetry. You can see if you can get one, because once you get one of the lines of symmetry, then repeat the pattern with regard to all of the vertices. So when we start here, we went from the vertex to an indented vertex. We can go from here to the indented vertex. A vertice, an outward facing vertice, to an inward facing vertice. Outward facing vertice to an inward facing vertice. And an outward facing vertice to an inward facing vertice. If you do a good job on your paper, it looks kind of artistic. To me, a not very artistic person. Anyway, letter F looks like a scalene triangle. No congruent sides or angles. And in fact, in this case, there's no way that we have any symmetry. We can't draw in a line and get symmetry on this particular picture. No way to fold that figure that maps onto the other side. In the coordinate plane, lines of symmetry are called lines of reflection. And we've kind of already seen it. If you reflect a figure over a line of symmetry, the figure will map onto itself. If you fold it in half, the right side will land directly on the left side. When determining if a reflection would map onto itself, you're simply looking for the lines of symmetry. So let's look at an example here. Again, the OST likes to test these questions, and watch out for the select all that apply here, because we need to go through each answer. We might only have one answer. We might have all 5 of them as an answer, or something more than likely in between. So the first one, we can probably visually look at. It says a reflection over the x-axis. If we take this graph and we fold it along the x-axis, will the top half of the graph land exactly on the bottom half of the graph? And the answer is yes. And because of that, this is going to be a reflection over the x-axis. The reflection over the line y equals x. Remember, if you don't know what y equals x looks like, then you've got Desmos. Don't forget about Desmos. The line y equals x goes from the bottom left corner to the upper right corner through the origin. And when we draw it here, it might kind of, sort of, look like there's a reflection over the line y equals x, but test it. And what happens here is, if we start with this point, my green dotted line's a little bit off, but it's really 1, 2 spaces up to that green dotted line, which would mean, since we went up to get a reflection, we're going to have to go to left. That means that this point here would have landed right there, and because it doesn't map on a point that is already there, this is not a reflection over the line y equals x. Thing is, if we can't reflect it over the line y equals x, we can't reflect it over the line y equals negative x. But by the way, where the line y equals negative x is, I'm trying to make it go through the origin, but it just has a slope of -1. And the same thing happens here. If we count from, say, this point, we go 1, 2, 3 up to that dotted red line. Then to get onto the other side of that red line, we're going to have to go 1, 2, 3 over here. And that point's not even on the figure. So C is also not a choice. So 2 more choices that we still have to work through, because this is select all that applies. A reflection over the y-axis. Well, the y-axis is here. If we fold this in half, will the right side land on the left side?
Yes.
Yes. And again, we were able to visually look at that and answer that question. And the last one here is a reflection over the line y equals -1. Again, if you get confused by those lines, type y equals -1 into Desmos, and you will get a picture that looks like this. But what we see is that if we fold our graph along that line, the top part of the figure will not land on the bottom part of the figure. So our only answers here in the select all that apply are A and D. For the most part, I think that you're familiar with that type of symmetry. The there's another type of symmetry that you may or may not have seen called rotational symmetry. And I've got a lot of words here. I think I can make it make more sense when we do our examples, but I do want to talk through the words just quickly. A second type of symmetry is called rotational symmetry. Rotational symmetry is when you can rotate a figure about its center and it will map onto itself. And part of rotational symmetry is something called an order. It's the number of rotations that occur to create rotation symmetry. Again, I'll show you that in our first and second example momentarily. The angle of rotation is the degree at which you can turn a figure and it maps on itself. So we're going to turn it somehow. And when we turn it, we want to come up with the same figure that we started with in the exact same place. The angle of rotation has to be less than 360 degrees. To find the angle of rotation, divide 360 by the order. Finally, a figure can have more than one angle of rotation because it can be rotated more than once. And actually now, finally, when finding rotational symmetry of regular polygons, and this is regular polygons, the order is the same number as the number of sides. For example, a regular decagon, well, a decagon has 10 sides. A regular decagon will have an order of 10 because it has 10 sides. But again, the words probably don't make as much sense until we see an example here. And it says, determine if the following figures have rotational symmetry. If yes, determine the order and the angle of rotation. And I'm going to slide this over for a minute because the board gets disoriented very easily on the left. But first of all, same picture as what we had on the front of our paper. We see that this is an equilateral triangle. And what we just said in our words is, when finding rotational symmetry of a regular polygon, it's going to be the same as the number of sides. So this is a regular polygon. We have 3 sides, so our order is going to be 3. And what I'm going to do, you don't need to do this on your paper, but I'm going to try to trace this triangle. And my triangle is not completely equilateral. Good intentions, but it's not quite. But what I can do here, because here's the rotation symmetry. What it says is I can rotate this graph. So I'm going to turn that. And again, my triangle's not quite right. So when I turned it, it should have landed exactly on the triangle. And what I just did is I did one angle of rotation. Well, if I turn it again, my triangle should have landed, if I had drawn it a little bit better on our paper, should have landed exactly on. There's a second angle of rotation. And then when I finish here, it lands again in this exact same place. So there is the angle of rotation. There you see the rotational symmetry, and the angle of rotation is determined by taking 360 divided by 3, which is 120. And I'm going to scoot that back over so I can see the rest of these. But so 3 and 360 divided by 3, which is the 120. Going to be a regular pentagon. This one will show up a little bit better in terms of our rotation, but we have 5 sides. And it's a regular pentagon, so our order is going to be 5. Again, you do not need to trace this. But this one will show up a little bit better. And we draw it. So here we're going to rotate. We rotate it once. Just a slight bit off. There's one angle of rotation. Here's another 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 angle of rotation. We can rotate that picture 5 times. So every time that we rotate it, what we're doing is we're going 360 divided by 5, which is 72 degrees. When we get to the heart, well, if I outline it, again, you don't need to outline it. It's not a regular polygon, but what happens here as we keep turning, what we want is we want this heart to land on itself, and it doesn't land on itself until we go all the way around. So we can say that it took us 1 full circle to go around, and our angle of rotation, well, there is no angle of rotation, because an angle of rotation needs to be less than 360 degrees. It takes us a full circle to go around, and a full circle is 360 degrees. So very quickly here, on letter D, here is our irregular polygon again, but we can't rotate it around. We could do the same thing that we just did with the heart. We could go around once, but it's going to take us a full time around before we get our same figure, before our figure maps onto itself. But stay here with me for the star. The star. We've got a point here. We've got a point here. Point here. Point here. Point here. And I didn't draw my picture very well, but watch for the rotation here. There's 1. Here's 2. Here's 3. Here's 4. Here's 5. So it goes back to these outward pointing vertices here. The order in this particular problem is 5. And this is 360 divided by 5. Once again is 72. And you can probably imagine here on our last one, the scalene triangle. We didn't even have any lines of symmetry in there. We also don't have any rotational symmetry in there, because it would take us the full time around to get back to that original figure. So I'm going to put the order as 1. Figures graphed in the coordinate plane also have rotational symmetry. Let's revisit the same figure from example 2. And this one's going to be a select all that apply question as well. In the diagram below, a regular hexagon is centered at the origin. Determine which of the following transformations would map a figure onto itself. Well, it's regular. That means that its order is 6 because there's 6 sides to a hexagon. So if we take 360 divided by 6, we get 60. And then what we can say here is, or we can answer the question based on that. I'm going to try to, oh dear, I'm going to start one more time. Trace this figure. And let's see if we can answer the question here. So we're going to turn. There's once. Here's twice. Here's 3 times. Here's 4 times. Here's 5 times. and then 6 times to get back to the original. Well, think about it. If we turn this, it's 60. If we turn this again, that's going to be another 60. If we turn this again, it's another 60. Another 60. Another 60. Another 60. We actually were able to answer at least one of those here, this one, from just filling in the 360 divided by 6. It says, in the diagram below, a regular hexagon is centered at the origin. Determine which of the following transformations would map onto itself. So the thing is, we went 60. Did we ever go a value of 90? No. Did we ever go a value of 118? No. But we did go a value of 240. It's a multiple of 60. We did go a value of 300. It's a multiple of 60. Notice also what you see is we had line symmetry in this problem from example 2, and now we have rotational symmetry in the same picture on this particular select all that apply multiple choice question. One last problem here. We've got a regular octagon is graphed below, and we want to determine which of the following transformations would map a figure onto itself. Select all that apply. Well, remember that an octagon has 8 sides, and so I want to start off with the order here, and the order is the order is 8, and when we take 360 and we divide by 8, we get 45. So if we look over here, in terms of our answers, we might be able to figure out one of them, maybe 2. But once again, as I try to trace this figure, and I'm close except for that top line. But let's look at this here, and we rotate. We want 45 degrees. Then we, oh, not happening here. Try again. One more. And we went 45 again. We went another 45. Another 45. And so forth. As we complete a full rotation here. And the thing is 45 a factor of 225? It is. In other words, what I'm asking myself is, if we divide 225 by 45, do we get an even number? And we do. And then, let's look at the 80. Well, 45 doesn't go into 80, so we can eliminate that option. I wonder about 270. 270 divided by 45. There, it goes in there evenly. So we can say 270 is an option as well. And then I'll erase my trace since it's not very good, but when we finish here, the reflection over the x-axis. If we reflect this picture over our x-axis, then our figure is not going to map onto itself. It's going to be down here. We're going to have this, and then we're going to have here, and so forth. We're not going to map over the x-axis. But if we look at the reflection over the line x equals 1, remember, x equals 1 is here. And if we count, if we pick a point, this is 1 space away from that green line, this is 1 space away from that green line. Or, I don't have a better point, let's look at this point. This point is 2 spaces away from this green line. This one is 2 spaces away from this green line. It looks like it is a reflection over the line x equals 1. And finally, if we look at this graph over the line y equals x, remember it goes through 0, 0. And the slope is 1 over 1. I know I talk oftentimes about going from the lower left to the upper right, but we need to go through 0, 0. So here is our line y equals x in this case. And we can visualize there that we cannot fold that picture and have kind of the bottom part of the picture. This part here is what I'm talking about. If we fold that over, it's not going to land on the purple and blue and aqua and green part of the picture. So our answers to this select all but apply are A, D, and E.